here on estimating bioshifts in a phylogenetic context. And this talk's a little bit different for me. For me at heart, it's really a biological problem, and it's a sort of conceptual problem. So I just want to highlight a few things that I think many people who are working on how we estimate biome shifts might be something worth considering. And so you'll see how simple this model is, but you'll see that it's potentially important. So here are biomes. Biomes are communities of species that typically are adapted to similar ecological and climatic conditions. And if you look at these biomes here, you get some impression of what types of environment species that you find there what pressures they might face. So, and you might not be surprised to find certain species in certain biomes. For example, polar bears in the tundra. And over time, it's conceivable that things like polar bears might shift into warmer climates, especially with climate change, and if they survive, they'll adapt to those climates, right? They'll adapt to new biomes. And so at heart, this is what these phylogenetic biome shift models are trying to get at, is on a phylogenetic tree, can we identify where and when those shifts occur? And can we identify the directionality of those shifts? And in a modeling context, it's essentially going to come down to, can we assign different probabilities to different types of shift patterns on those trees, right? So here we have two, where on the left we're saying ancestrally you're warm and you tend to stay in that warm state for a long time. And on the right we have a fairly early shift into a colder biome. Now, another peculiarity is that while you might not be surprised to find a polar bear in the tundra, you might be surprised to find one in the jungle, right, or in the tropical forests. And there's lots of reasons for that. One of them is they don't seem to be particularly well adapted to the tropics, and that's true. I mean, you might think that if you found a polar bear in the tropics, then you find the tropics just littered with polar bear corpses. But you don't really find these zones between the tropics and the Arctic where polar bears are dying. Why are you guys laughing at polar bears? So this is really the heart of the problem. What's going on there? Well, there seems to be some geographical opportunity for shifting between biomes. So you can't readily access these tropical biomes from the Arctic, right? And this wonderful paper in 2014, written luckily by the co-authors of this paper, we're highlighting this issue among other issues when you're trying to estimate these probabilities, or at least develop conceptual models for how you might transition between biomes. And so this, in my opinion, this early paper was a conceptual paper that even went as far as to sort of have little probability statements that said, I hope somebody can fill that part in. So luckily I ended up in Michael's lab and we started to work out some of these details. And so what I'll be presenting is mostly a statistical approach that you might be able to estimate the effect of geographical opportunity. And in particular, I'll focus on viburnum. So viburnum is a group of about 165 flowering plants. And among living viburnum, most are found in these warm temperate forests that experience some rare freezing. The next largest proportion of them are these cold temperate forests where they experience prolonged freezing for several months. And then finally, just a few persist in these tropical regions that experience no freezing whatsoever. There's other differences there, but that's the important part. Now let's look at where they live on the planet. Well, let's say you just took this pie chart. Let's look at the numbers of species you find in different regions. Their diversity today is centered in East Asia, and you find a fair amount in other regions such as Southeast Asia, North America, and Latin America. And let's take those biomes that I showed you earlier, the proportions of lineages in different biomes, and let's just assume that you find the same number of species proportionally in each region. Well, you end up with something like that. And for many of you, you might be a little dismayed to find that Europe has many tropical forests, or North America has many tropical forests, or Southeast Asia has these large proportions of cold, temperate, adapted viburnums. That seems strange. Well, in reality, you have this interdependence between the region and the biomes that you find them in, and it's one that makes some sense. You find more warm and tropical things near the equator, and you find more cool things near the Arctic, right? So that seems to be something that would be important to take into account for our models. And the real trick here, in my opinion, people have worked on that part of the problem, and it's an important part of the problem. But there's another part of the problem, which is the actual geographical opportunities themselves will change over time because the lineages evolve, but so do the biomes evolve. So if you're thinking about where are biomes in space and where do they exist in regions, you also have to think about the availability and connectivity of the biomes over time. Because even though you have northern hemisphere dominated by cold temperate forests today, it hasn't always been that way. So to break this down, let's just look at two fundamental parts of this very simple model. The first one is we want to talk about how do biomes evolve structurally, and second, we want to talk about how do lineages evolve within those biomes. So the two parts for this first aspect are well, we're going to say that each region can contain some number of biomes, and that the regional biome structure can change with time. So let's dig in there. First, this is the anatomy of what I'm about to show you. Essentially, we'll have a series of these adjacency matrices, and each adjacency matrix will represent something about the availability and the connectivity between regions. And here I'm highlighting the mid to late Eocene and focusing on tropical biomes, for example. And you can ask me how I did this. I did it tediously. There aren't good quantitative reconstructions, in my opinion, for structures of biomes over deep timescales. That's just the world we happen to live in. So now let's think about different ways we might structure biomes or regions over time according to different features. So let's just assume that all regions are always connected. So I'm just going to call this the null model. That's not too enlightening. Now let's look at geographical constraints. So I'm saying that regions have to share some marginal amounts of terrestrial connectivity, or at least be relatively close, in order for species to easily disperse between regions. Well, turns out the Cenozoic, here this is between the late Cretaceous and the present, Cenozoic is not that exciting in terms of major tectonic events, in my opinion. You have some cool stuff towards the end, like the Isthmus of Panama forming and the North Atlantic land bridge closing, but you don't really have that nice Gondwanan vicarious, the charismatic mega process business or whatever. So now let's skip to a different aspect of geology or geography that is more fascinating during this time period. Let's look at three major mesic forest biomes: tropical, warm temperate, and cold temperate biomes. Well, what's going on there? We have much more activity than you do with that blue, the brown column, pardon me. And you pick up two major dynamics during this time interval of about 100 million years. So early on, you have this northern expansive boreotropical forest with incredible amounts of opportunity for shifting biomes to warm, temperate, and tropical biomes. You also have enhanced ability to disperse between those regions because that forest is everywhere. But once you hit the Oligocene, you start to enter this colder and arid, more arid world, right? And that's when you have the rise of these cold, temperate, and boreal forests. So if you were to ask me, how likely do you think it is to find a cold, temperate lineage persisting in the late Cretaceous, Paleocene, Eocene? I would say not very likely, just looking at this structure. Now, you might not agree with this structure being the exact correct structure, but let's just imagine that this is a reasonably good structure, and we can quibble about this structure in particular later. I just want to say that potentially has an effect here. So now let's think about how lineages might evolve among the biomes. And there's three parts to this. First, we're going to say that lineages have both biome and region states, that you can shift between biomes, but you can also disperse between regions, and that happens in geological time. And then finally, the event rates themselves for those two different types of changes will depend on geological time and on that biome structure I just mentioned. So let's look at compound states. I mentioned earlier there's 6 regions I'm interested in. Let's also think about 3 biomes here. And if we multiply those, then we get 18 compound states. And those are just combinations of biomes and regions, nothing crazy. What I'm going to do now is basically use a variant of the Pagel's 94 matrix where I have correlated characters. And it'll have this sort of block structure where on the block diagonal, that's going to correspond to dispersal rates between regions. And then off diagonal, we'll be talking about shifts between biome pairs. And basically those 2 white boxes mean I'm disallowing transitions from tropical directly into cold forests. You have to go through warm temperate forests. You could change that if you like, but I think it's fine. Now let's just evolve a very simple compound state with a very simple rate matrix. This reflects that null matrix I showed you guys earlier. And let's suppose we start in the warm East Asian state, which is red there. So let's just look on that row for the rate matrix, and we start there. And some amount of time elapses, and then suppose there's a dispersal event. Well, I said that central block diagonal, those are the dispersal events, the ones in red. So here, we just happen to sample or simulate a dispersal into North America. But we still retain our biome character for this model. So we're saying that you have to do one or the other at any moment in time. Let's evolve a little more. So now we're in a different row of the matrix. And this time we shift into the off diagonal. That's the biome shift part. And here we've now gone in situ from warm into cold temperate forest in North America, right? So you're shifting biomes locally, and so on and so on, and so on. All right. So I'll just highlight some of the features of this model. So first, the null model is quite boring. And it essentially says that there's a time constant biome shift rate and a time constant dispersal rate. And 2 events can't happen in one moment of time. That's all that's saying. And just notice that the time is changing at the top. That's it. Nothing happened. Okay. Now let's look at a process that cares about terrestrial connectivity among regions. So we're adding a new thing. This is in the red term here. That's representing that brown column of adjacency matrices. So we're saying that over time, we're going to say that there's some rate modifier that's associated with different time intervals, m. So time-varying dispersal rates. And like I said, not much happens until maybe you hit the Oligocene. But again, it's not that exciting. It's not a very dynamic time. And that's something that we want to reflect in our model. Finally, let's look at this third class, and this is the most exciting one. In this case, we're saying that both the biome shifts rates and the dispersal rates will be functions of time, functions of m. And it also matters where that lineage is, both in terms of its biome and in terms of its region. That will affect how easy it is for it to shift or disperse. So we're really having these two processes interact now. And look at that. You see it, if you look at the middle row of diagonals, those are lineages that are in warm temperate forests, for example. And you can see that in the older periods of time, you have much more connectivity in the north. And as you come towards the present, it's more fragmented. So you can kind of see it goes from a block into something that's more diagonal. How am I doing for time? Not great. Okay, so here, we're going to take a weighted average of those matrices because you don't actually know which process is acting on your clade. So this is a big problem. Each clade will have different subjectivities to biomes and regions and dispersals and whatnot. So I'm going to really fly through these next slides if you'll excuse me. The viburnum data set I'm working on, it has 110 species. They originated in the late Cretaceous, and these are the 3 biomes and 6 regions I mentioned earlier. And that's the familiar biome structure that also was referenced. What we're going to do is have 3 sort of experiments we'll run. First, we're going to assume that all structure always was fully connected at all times. So this is what most people do currently when they're modeling biome shifts. Let's take something slightly more advanced and assume that all biome structures reflected modern biome structure over all times. And this is the next stage of advancement of what people do when thinking about biome shifts. In the third case, let's just incorporate everything and see if we get any differences when we do reconstructions under these models. And we do. So this is hard for you to see, so I'm just going to highlight one piece here. And that is, for the paleobiome model, you get warm and tropical ancestry, but for the other ones, you either get cold and warm or warm and cold ancestry. So when you ignore paleobiome structure, you're enriching for colder biomes. And the ancestral state estimates reflect that too. So that's all that's showing. It's a little concerning that by swapping out your biome structure, you get different ancestral state estimates. And I'll just say that both the paleobiome model and the modern biome model think that you have a lot of confidence that it's fitting the model correctly. So it's really thinking that the biome weight is important. The last thing I'll mention is that let's try to get a sense of how correct and where is our model failing. And what I'm going to do is basically score the percent of the tree length that is mismatched against this structure on the right. And to do that, just look at those 3 exclamation points will illustrate a part where there are no cold temperate biomes at that point in time. And I can do that also for a different stochastic mapping and compute it that way. And I can basically summarize this over the 3 biome models, and lo and behold, these modern and known models, when you ignore paleobiome structure, are greatly enriched for these cold temperate origins. And that doesn't seem to make much sense given what we know about the paleobotanical record. So in summary, basically what I've done is, all I'm trying to say is that if you're reconstructing ancestral biomes, you can, and I think you should, incorporate that information into your models, and we shouldn't be surprised that our estimates are sensitive to it. This is basically what I did for the model. This is a very simple model, but if you're familiar with model structures, this can be imported into other much more sophisticated models. And finally, thank you to everybody.